Hello, everyone. My name is Yunze Xu. I'm a software engineer from Stream Native. Today, I'm going to talk about take Kafka Pulsar to production at internet scale, improvement made for Pulsar 2.8.0. First, in this talk, I will first introduce why we need Kafka Pulsar. Then I will give a brief introduction to KOP. Next, I will talk in details about what's new for Pulsar 2.8.0. At last, my partner from Tencent will talk about the practice of KOP in Tencent Big Data. First, let me introduce myself. I'm a software engineer from Stream Native, and I'm an Apache Pulsar committer. Currently, I'm the core maintainer of KOP. My GitHub ID is Beware My Power. First, let's look at the Kafka and Pulsar for pub/sub scenario. In this scenario, they have much in common. Producers publish messages to a topic. Then consumers can subscribe a topic. After that, they can receive messages from the topic. Usually, a topic could contain many partitions. Each partition can be processed in parallel. And Kafka and Pulsar both have broker. Broker is responsible to manage these topics. Then let's see the difference. Since this is the talk for KOP, I will not talk too much about the difference. But the core difference is the storage. Kafka's broker receives messages from client and write the messages to the local disk page cache. But Pulsar is different. Pulsar has an extra storage layer named bookkeeper. Each node is called bookie. Broker receives messages from client and then send messages to bookies. Kafka fans will say Kafka is simpler and faster, and this extra storage layer is a trade-off. But the trade-off also brings many benefits. For example, Kafka's broker has leaders and followers. Followers replicate messages from the leader. However, there is no leader or follower in bookies. Or we can say each bookie is a follower whose leader is the broker. So bookies and brokers are stateless, which makes scaling out very fast. I'm not going to say Pulsar is better than Kafka, but if you have some problems using Kafka, then trying Pulsar is a good choice. So imagine your infra teams ask this question: could you change your existing code using Pulsar? The response is maybe the first, sorry, I have other important things to do and I don't want to change my code. Or sorry, I use Kafka connect to an external system, but there is no connector to Pulsar. Or the response is maybe I'm okay, but I write PHP. It's the best language of the world. We should admit that Kafka's ecosystem is really good. So migrate from Kafka to Pulsar is not an easy thing. Therefore, Project Handler was born. From Pulsar 2.5.0, it introduced a component named Project Handler. Look at the architecture. Kafka Project Handler was loaded by the broker, and it can access all the components of the broker, like the managed ledger, which uses a bookkeeper client to access bookie. And it could also access the load balancer, which determines the topic ownership. And it can also use the Zookeeper cache to access Zookeeper for metadata. Now, so how to use or just say enable KOP? It's really simple to use KOP. First, you should put the NAR file on the protocols directory. Then configure the broker point conf or standalone configuration. Then start the broker. Look at the configure. The messaging protocol is required. It should be Kafka. And we should, because Kafka topics are all partitioned, so it's better to configure allow auto topic creation type to partitioned. Then listeners is also required. It specifies the address that KOP service listens on. Finally, from Pulsar 2.8.0, KOP need to configure the broker entry metadata interceptors. For quick start, you can just configure KOP on a Pulsar standalone. KOP supported many clients because it supports Java Kafka protocol from 1 to 2.6. So, but the core tests are based on Kafka Client 2. Following clients are verified by basic end-to-end tests like Java client and other Kafka-based clients and Golang Sarama. You can use Pulsar standalone with KOP for a quick verification of your Kafka client. Then you can see whether your client was supported. So how did it works? Kafka on Pulsar actually implements an interface named protocol handler. This is the steps when a broker loads Kafka on Pulsar protocol handler. First, it will load the NAR file from the protocol subdirectory and use the accept method to validate it. Then it will call initialize method to configure the protocol handler's configs. And the next is the most important steps. Look at the start method. It accepts a broker service argument. Broker service is a class in Pulsar broker. It manages all brokers' resources. For example, the all connected producers and the subscriptions in this broker, and the topic and the broker's owned topics and the associated managed ledgers. It also has built-in admin and clients with broker's authentication. So it has therefore all things brokers can do, KOP could also do. At last, it calls new channel initializers to bind the address like 9092. Then the Kafka client could connect it to this port. As we have said before, Kafka and Pulsar both have topic and partition. In Kafka, topic is a short string, and the partition is an integer. But in Pulsar, the topic name is an URL. The first part is whether to persist the message, and the second is the tenant. Third is the namespace, because Pulsar supports multi-tenancy. So I noted I noticed that Kafka also supported multi-tenancies recently. Then the left are the short topic name and the partition suffix. Therefore, we can do a simple map from Kafka's topic and partition to Pulsar's topic name. The default tenant is public and the default namespace is default. So assuming there is a Kafka topic named my topic, it will be mapped to the persistent public default my topic. Here are the left cases, and you can specify another tenant or namespace, so you can use Pulsar's multi-tenancy. And the Pulsar could handle the produce and fetch requests by following. First, it will find the persistent topic. Persistent topic is a class of Pulsar broker, as well as the broker service. When you find the persistent topic for produce request, it will first encode the memory record to raw bytes. Then use the managed ledger to write the bytes to bookie. And for fetch requests, first read bytes from the bookie and then decode bytes to memory records. At last, the memory records will be wrapped into a Kafka response and sent to the Kafka client. There is a case that what if failed to find persistent topic? KOP will return a not leader for partition error. It will trigger client retry behavior, so the client could send the metadata request again and find the topic's owner broker. Now let's see what's new in 2.8.0. The first is the continuous offset support. Before 2.8.0, there is no way to implement a continuous offset. Before 2.8.0, it maps message ID to offset, but it has many problems. My partner will talk about how we implement the continuous offset. So I just skip this chapter. And I will talk in details about Kafka's entry formatter and the heap memory optimization, which is related to the performance improvement. Besides this, KOP also exposes this matrix for all Kafka requests, so we can see requests latency and other metrics. And from 2.8.0, KOP supports OAuth2 authentication and has more support for Kafka's admin client, like create topics, describe groups, and delete topics. And also KOP exposes the advertised listeners. This is convenient for some third-party proxies like Envoy Kafka filter. Okay, let's first see the Kafka entry formatter. Before 2.8.0, when we receive a message from the bookie, we will first decompress the batch. A batch contains many single messages. So after it's decompressed, we need to get single messages from the batch. After we get all single messages, we still need to convert each single message because its format is Kafka format. We need to convert it to Pulsar format. At last, we need to reconstruct the metadata. So, is it necessary? I see if a user migrates a service from Kafka to Pulsar, the clients should be all Kafka clients, and there are no Pulsar clients. From this point, KOP 2.8.0 adds the config named entry format. The default entry format is Pulsar. The behavior is as I said before. But if you want a better performance, you can configure the entry format to Kafka. Then KOP will create an internal classes which implements the interface entry formatter. When we handle the produce requests, it only adds the metadata header and keep the original bytes of Kafka's memory records. When we handle the consumer fetch requests, the process is a little more complicated. First, KOP will fill the offset and the length fields of each entry, then merge these entries to a byte buff. Finally, the byte buff will be converted to the memory records and sent to Kafka client. So there is a limit that for a topic, we could use the Kafka producer to produce and the Kafka consumer to consume. Also, we can use a Pulsar producer to produce and the Pulsar consumer to consume. However, it cannot use a Kafka producer and a Pulsar consumer, or use a Pulsar producer and a Kafka consumer on the same topic. But we still add a Pulsar message metadata header before the Kafka message. In KOP, it adds a property to mark the message's format is Kafka. So in future, we'll handle this property in Pulsar's broker or client side. After that, the messages produced by Kafka producers can be consumed by Pulsar consumers. Another improvement for the performance improvements is the heap memory optimization. Recently I performed the performance test. When I tested a producer, I found the heap memory increased fast and triggers GC frequently. The heap memory increased very quick. However, Pulsar uses direct memory for messages. This should not happen. That is, say that the messages should be allocated from the direct memory. But from the dump analysis, we can see there are a lot of messages in heap. Each byte array is a message whose size is 1 megabyte. You can see the byte. There are many repeated byte arrays. Each byte array is a message. Sherlock Holmes says, once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. So we use the direct memory for messages, but we can see it's still allocated from the heap. Finally, I found the reason. When a native composite byte buff that contains more than one component is converted to an NIO buffer, it will be created in heap memory. Look at the red line. It uses byte buffer allocate method. We can't specify another allocator, so it will always be allocated from the heap memory. After looking the code, I found the cause. First, when we write a composite byte buffer to bookkeeper, the bookkeeper's JNI-CRP32 algorithm needs an NIO buffer as the argument, so it will convert the composite byte buffer to the NIO buffer. And when KOP handles fetch requests, it uses a composite byte buffer to merge multiple byte buffs. But when we need a memory records to Kafka client. The memory records internal byte buffer is the NIO buffer. So we need to convert it it to NIO buffer eventually. After knowing the cause, the fix is simple. In bookkeeper side, we compute the checksum for each component of a composite byte buff instead of computing the composite byte buff CRC32. And in KLP side, we just allocate a new buffer in direct memory to merge buffers. We can see the compare before this optimization, the heavy memory increased very fast. But after that, the heavy memory is increased very slow. But after the previous fix, when the consumer calls pull method in a tight loop, the heavy memory still increased fast. And I found the increasing speed is not related to produce rate. That is, there is no difference between 50 megabytes and 200 megabytes per second. Let's see the fetch request handler. First, we need to find the partition topic, and then we read bytes from bookie. Finally, decode bytes to memory records. However, a fetch request can contain many partitions. So before 2.8.0, it will first find all partition topics and collect to a list. Then read the messages of each partition and collect to list. And it uses maps to cache middle results. Finally, decode the list of messages and create the response. We can see many lists and maps are created, but they are not allocated from direct memory. So we already use the Lattice object pool for rich fetch request handles context. The temporary list and maps are not allocated from pool. So we just fix it by processing each partition's fetch in parallel. So there will be no middle, no list and map allocated from heavy memory to cache middle results. After this fix, we can see the GC interval increases from 90 seconds to 120 seconds. So there is still room for fetch request optimization to reduce GC because 2 seconds per GC is still too frequent. So let's see the performance test. I run the performance test on AWS using open messaging benchmark. Here we just compare the Kafka client and the Pulsar client in the same KOP cluster. There are some blogs that compare performance of Kafka and Pulsar, but we KOP is for users that want to use Pulsar, but they don't want to change client. So if the performance of Kafka client is close to Pulsar client, we can say KOP is ready for production. First, I test the latency. Here is the producer only for a topic. Batch size is 1 megabyte, and the max batch latency is 1 milliseconds, with 100 megabytes per second produce rate. From the latency, we can see the gap is about 3 milliseconds. It's okay because there are still some overhead. For example, we need to validate Kafka records before writing to Bookie. But in Bookie side, Bookie still computes the checksum. And the network's frame design also has some problems like request queue. From the right picture, we can see the produce latency is for the top. Produce latency is the latency that KOP produces. It only takes it only took about 4 milliseconds, so it's not too large. And the encoder latency is about 1 millisecond. It includes the validator of Kafka records. The message published latency is just the latency writing the records to booking. Then I test the case that both producer and consumer are created. From the right picture, we can see there is a crest in 99% published latency. It's because I said there is still room for fetch request optimization to reduce GC. You can see there the crest happens at 140 seconds, and we will have a GC per 2 seconds, so it's normal, and we should handle reduce the GC in future. For the throughput, the disk throughput, first I test the disk throughput. We can see the throughput of NVMe SSD is 800 megabytes per second. So we should adjust bookkeeper's config to avoid files are rolled too frequently. The default general max size is 2 GB, and now we change it to 20 GB. So we create 100 partitions and 2 producers, 2 consumers with 800 megabytes per second. We can see KOP throughput is about 88% of Pulsar. And the publish rate and the consumer rate are close to Pulsar. Here are the metrics that are added to monitor the publish latency, fetch latency, and out bytes and in bytes. And there are more details. We can go to GitHub to see more details about it. In short, KOP will be generally available for production from 2.8.0. For these following 3 points, first is the continuous offset, which will be introduced by my partner, and the performance improvement and the metric support. In future, we will perform more improvement on performance and support Kafka client with lower version like 0.10 and 0.11. And we currently KOP only support authentication, but does not support authorization. So we will support authorization. Now my talk is over. Let my partner take over the talk.
Hello everyone, my name is Zhang Dawei. I'm a software engineer at Tencent. And I'm also an open source enthusiast. For now, I am the code maintainer for Kafka and Pulsar, aka KOP, and a committer for Apache Incubator Inlong. Today, I'm going to share our practice of Kafka and Pulsar in Tencent Big Data. Okay, here is the agenda. At first, I will introduce why we chose KOP. And after that, I will list some problems we have met along with testing and using KOP. And the following 3 sections will describe how we resolve these problems. And the last part will show an example that we use KOP in our product environment. At the beginning, let me introduce some backgrounds. I come from the method queue team, and our team is responsible for the development of the MQ platform and aim to provide stable and reliable service for all the development in Tencent, and also some users on the cloud. We now provide 3 types of MQ for different user scenarios. The first is that user has massive data and requires high throughput. We support this scenario by TubeMQ, which can process more than 60 trillion messages per day. And we also open sourced it to the Apache Software Foundation. And the second scenario is users has high requirement for data integrity, consistency, and reliability. We provide Pulsar to support these users. The last and the latest is KOP. We provide KOP as MQ choice for Kafka protocol users. Why we choose KOP instead of Kafka for Kafka protocol users? Here is some reasons. The first is that Tencent has been promoting open source and collaborations for the past few years. The purpose is to unify the tech infrastructures. In this progress, we found that some users build their own Kafka cluster. At the beginning, Kafka ran well, but with the growth of the business, Kafka cluster getting larger and larger. And then Kafka is becoming very difficult to operate and maintain. For example, when there are lots of topics and partitions, the performance will decrease. If you want to expand the broken node, Kafka needs to copy data to the new node. Therefore, these Kafka users want to replace Kafka with Pulsar, and especially they want to do this without changing their code. Another reason that we chose KOP is that we all know KOP reveals most of the capability of Pulsar, such as seamless expansion, convenient disaster strategies. And the most important is that KOP allows users to migrate from Kafka to Pulsar without changing code. So we finally decided to choose KOP for Kafka protocol users. Actually, we participated in the development of KOP for a long time, so we have encountered many problems. Here, I list some of them. For example, performance both for produce and consume. Kafka admin CLI tools are not supported well. Some commands are not supported, and some have bugs. And KOP have no metric for both produce and consume. And KOP is not very stable. Out of directory memories happens frequently. And when you reboot the KOP node, you will find it getting slower and slower. And in KOP, we can't get the accurate lag information for Kafka consumer group. Another fatal problem is KOP cluster will not be available after running for a long time. Some of these problems have been introduced by Yunde, for example, the poor performance and how to improve it. So I'm going to talk about some arrests and how we resolve them. The first is how to speed up the reboot, and the second is how to throttle producer to prevent broke from OOM. And the third is how to enable continuous offset for KOP. Okay, let's talk it one by one. As described, KOP reboot will cost more and more time. As we all know, Kafka has an offset topic which contains all data for consumer group and offset, and so does KOP. KOP also has an offset topic for Kafka consumer group and offset, and data added to this topic is never be removed or cleaned. And when KOP restart, it will load all the data from this topic to rebuild the consumer information for Kafka consumer group. So the more data in this topic, the more time the reboot will cost. Here we have 2 ways to resolve this problem. The first, we set the retention for this topic, which can limit the max retention time for data in offset topic. And once data is expired, it will be removed. And second, we add a compact configuration for offset topic. And this can compact data by key, and the key is a consumer group. By this, we can guarantee that data in this topic will not be too much, and the reboot time will not be long. Okay, let's see the second problem. QP node is going to out of direct memory very frequently. When this happened, we found that a lattice bytebuf object occupied most of the directory memory. This is caused by Kafka producers and producer requests more faster than broker can write to booking. And so many entries are held by the broker, and finally it will be OOM. The way to resolve this problem is enable producer throttle in KOP. This is a function that already supported in Pulsar broker for Pulsar producers. Okay, let's see the mechanism in Pulsar broker first. Every broker is configured with a max public buffer and a counter to calculate the memory usage. The counter will be increased when broker receive requests from producer and will be decreased after the entry is written to booking. If the counter is bigger than the max public buffer, which means broker hold too much producer request that has not been read to booking, broker will block all the producers to avoid broker OM. In QP, we reuse the mechanisms of Pulsar. QP will reuse the max message public buffer and also the counter. So the counter will be increased when QP receives card from Kafka producer and will be decreased when this card has been written to booking. If the counter is bigger than the max public buffer size, the broker will block all Kafka producers and Pulsar producers. After enable this feature, QP and Pulsar broker share the same max public buffer size and can avoid OM caused by produce too fast. Okay, let's see the last problem. At first, let's see how Kafka and Pulsar find a message. Kafka uses a 64-byte base offset to locate a message, and Pulsar uses a message ID, which contains three parts: ledger ID, entry ID, batch index, to search an entry. Since QP support Kafka protocol at Pulsar broker, it should have the capability to map the Kafka offset to Pulsar message ID and vice versa. Let's see how QP do the mapping in the original data. It split the 64 bits into three sections. The first 20 bits for ledger ID, and the middle 32 bits for entry ID, and the last 12 bits for batch index. By this way, we can deal with the gap between Kafka offset and Pulsar message ID. But if you run QP for 10 times, you will see the defect of this design. First, you will find the offset is hollow. This is mainly caused by the ledger rollover. Once ledger rollover, the next ledger ID may be not continuous. This is not friendly to the third-party systems. It's dependent on continuous offset feature. And also, when you describe consumer group by Kafka admin CLI tools, the lag of consumer group is not accurate. And secondly, ledger ID only have 20 bits to represent, so it will overflow quickly. Then QP cluster will not be available. And entry ID batch index also can overflow. This may lead to the offset not accurate. If we want to resolve this once for all, the best solution is allow Pulsar to support continuous offset feature like Kafka. Therefore, it's necessary to add some information keeps offset. for each entry on the broker side before added to booking. The design is as follows. Each topic partition has a monotonically increasing offset starting from 0, which means the offset of the first entry in this partition is 0, and the offset of one entry plus the number of messages in this entry is the offset of the next entry. Offset is added by the broker, and the broker can find the message ID according to a given offset, and also broker can find the offset by a given message ID. Okay, let's take a closer look at the implementation of the continuous offset feature in Pulsar side. In the original protocol Pulsar, producer sends the data to broker. Data contains protocol head and payload. Protocol head is used to distinguish request types. Head and payload contains metadata and payload. Now, we need to add some new fields to keep the offset in new protocol. These fields we call it broker entry metadata. It contains 3 parts. First is broker entry metadata magic number. It is used to identify whether this feature is on. And the second is broker entry metadata size. Record the size of the broker entry metadata. And the last is broker entry metadata, which is the serialized broker entry metadata content. And head and payload is the original byte buff that contains metadata and payload. You can see we put the broker entry metadata before instead of after the head and payload here. This is because, firstly, the broker entry metadata is an addition for the origin protocol, and it can carry the offset information without serialized or deserialized protobuf message metadata built from the producer. And second, if we put the new fields after the head and payload, we can't know where the offset for the newly added field, since we don't know the length of the payload. And also, field after the payload will change the checksum, which means we have to calculate the checksum one more time. The message process logic before and after is shown in this diagram. A producer client sends a message to the broker and pass by Pulsar decoder only metadata and payload left. Originally, this metadata and payload we call message will be written to bookie directly, but now we will add broker entry metadata about the metadata and payload, then write the whole byte buff into bookkeeper. So the broker entry metadata is kept together with the original message in bookkeeper. After we support broker entry metadata at Pulsar broker, the last step for continuous offset is how to process Kafka requests. Mainly include 3 types of requests. The first is producer request. Once QP receives a producer request from Kafka producer, QP will build a new broker entry metadata, which contains offset information, and then QP will put the broker entry metadata ahead of the original message, and then write the whole message with broker entry metadata to booking. The second is fetch request. Once QP receives a fetch request from Kafka consumer, it will pass the offset in this request and find the message ID for this offset, and then build a cursor based on this message ID and read entries from booking. And at last, we will return the fetch response to Kafka consumer. And the third request is list offset. If QP receives a list offset request from Kafka consumer, they first get the timestamp from the request, and then find an entry by this timestamp. And after getting the entry, it will pass the broker entry metadata from this entry. And at last, it can get an offset from the entry metadata. Okay, after all this, POP can support continuous offset like native Kafka. In Tencent, there has been already several businesses run on QOP now. Here is an example. This business has a match-in rate is about 100,000 per second. Okay, that's all my sharing. Thank you.